Hello dear students, welcome back to our YouTube channel School for All. So today we'll proceed with part 2 of our full correction of the Northwest Regional Mock 2026. So the part 2 I will guide you how to solve and answer stations, the four stations of the Northwest Regional Mock. So we'll start by station 1, determination of the density of the material of a candle. So as I said, when you are on your mainstream, before going and collect the data, first of all know what are you going to collect. So first of all, understand the station, you know what you are going to collect. You start feeling, you feel, you put your diagram, you do your procedure, you do your observation. You leave the space for the observation, you do your processing, precaution, then for the conclusion you leave space. So after filling that now, and since you know already what you are going to collect, you now go at the level of the station, you take your observation. Your observation is the data collection, then you come back on your mainstream, you fill all this, and you have all your marks. So that's exactly what you're supposed to do. As I said before, you're not wasting time at the level of the station. The station is not for all, the station is for every student, it's not only for you. So you are going there, you take what you're supposed to take, you come back on your mainstream, you fill it. So let us start with our station 1. Now I will take my rough paper. I know that if I want to find the density of the material, that is the candle, I know that density is the mass of the candle divided by the volume. So that is what you know from the inference. Density is mass of candle divided by the volume. So I will need what? I will need the mass of the candle from where I will collect from at the level of the station. I will need the mass of the candle. Now from inside the volume, I know that the volume is the volume of a cylinder by radius square h. Is okay. Now I know that pi radius square h. I know that, but r is the same as diameter on 4. It means that another data that I need will be what? Will be the thickness. That is the diameter. It will be the thickness. That is the diameter of what? Of the candle. And I will also need h. Which is the height. So before going at the level of the station, you should know what you are going to collect. So for station 1, I need the mass, the diameter, and the height. Okay. So let us fill it before we go and collect our data. So here, I'm supposed to do a diagram, is 2 marks. So here you are not supposed to make a word. No, you are illustrating only what you are doing at the level of the station. So you can draw your candle. You can draw your candle like this. You know that a candle looks like a cylinder. You can draw something like this to represent the candle. We all know that it looks like a cylinder like this. Then from here you represent now what you are measuring. You are measuring the length of the candle. You present what you are measuring. You are measuring the length of the candle like this. You name it h. Yes. You are also measuring the thickness of the candle like this. That is the diameter. This is the diameter. You name it d, diameter. And you name this one the candle. Yes. So that is it. And you also, I think you also measure the mass. You also measure the mass of the candle. You can draw a spin balance like this, a scale balance, or electronic balance, depending on the balance that you are having. Now here it was a scale balance. Yes, you can use a scale balance to represent how you are measuring the mass. Something like this. Okay, so you are illustrating only like this, something like this. Then you put 0.02200 grams. Okay, so this is the balance. Put it, candle, and all those things. That is it for the diagram. Now we now proceed with the procedure. Okay, For the procedure, what are you going to write? You are writing what you are doing at the level of the station, what you will do at the level of the station. So you will write the mass. So you write the mass of the candle. The mass of the candle. The mass of the candle is measured. The mass of the candle is measured with a scale balance. With a scale balance. So that is it. What are you doing next? What are you doing next? You are also measuring what the length of the candle. So we are measuring the length of the candle. The length of the candle. The length of the candle is measured. Is measured using what? What are you using to measure the length of the candle? It's measured using a ruler. Using the ruler. And the last thing we are measuring is the diameter. So the diameter of the candle is measured. Now make sure you measure the diameter of the angle twice. Is measured twice at two different positions. Using a vernier caliper. So that is it for your 2 marks. So you are supposed to mention that you are measuring the mass using a scale balance, you are measuring the length using a metal rule, you are measuring the diameter of the candle using what? A vernier caliper. Now at the level of the observation, you will leave space, but you can wait. You know that you need the mass of the candle, so you need the mass in grams. You can do a small table here for your mass in grams. You need the length. Of the candle. You need the length of the candle M. You name it M in grams. Here is M. Pardon, here will be H. No. Let us name it H here. The length is the height. H measure in grams. Here will be M measure in. What am I saying? We need the length H measure in centimeters, because we are using a metal rule, a ruler. Here we need the mass M measured in grams. We also need the diameter. Which is D, and that diameter is measured in what? We are using a vernier caliper. Our vernier caliper surely will be in millimeters. Okay. So that is it. So there is your table that you come out with. You measure. Now we are measuring the diameter 2 times, so you can name this one D1, then here D2. So that is it. Name this one D1, D2. Then here we are taking the average. So this D average. We will come and calculate the average here easily. Now for the processing, I know that the density. This thing you are doing fast. Density of candle equals to mass of candle divided by mass of candle in bracket M divided by volume of candle in bracket V. So it is M all over V. Okay, so let me divide it like that. Now I know that V is what? V is pi diameter on 2 all square H. So we have the formula will be pi diameter on 2 all over 4 times h. So this implies the density that we are calculating is simply equals to 4 m, which represents the mass, divided by pi diameter square h. So therefore you leave enough space to come and compute. That is all. You leave space to compute what? To substitute and come up with the density. Okay. Now for the precaution, you don't waste time for precaution. You can say make sure that the diameter is measured twice and the average calculated. So you can say the diameter is measured twice. As I was saying, we are not sure that the candle is having a cross-sectional area. The cross-sectional area of the candle is constant all through. So it's better to measure it twice at two different positions. So the diameter of the candle is measured twice and average calculated. An average calculated to reduce random errors. So that is it. Then for the conclusion you write density. So therefore density equals to, that will be the conclusion. So after filling like this, now let us now move at the level of our station to collect our data, to come and put it here, and then compute the numerical application, and then we'll come out with the density. So that is it. Okay, so then now we are on station 1, which is asking us to determine the density of a candle. Now you are provided with a candle of uniform cross section, a vernier caliper, a ruler, and a balance. So this is our balance, this is the vernier caliper here, this is the candle here, and this is our metal rule. Okay. Now we all know that what from the inference that we did already, the inference here is to find the density of a candle, and the density of a candle is mass divided by volume. So you already know the data that you are coming to collect at the level of the station. We are collecting what? We need the mass. That is the reason why we are having the balance. We need the length of this candle, is the reason why we are having the metal rule, and we need the diameter. The diameter of the candle is the reason why we are having a vernier caliper. So I will start by finding the diameter of the candle. Now, when we were doing the mainstream, I already explained how to use this kind of vernier caliper. So I will apply it here directly. So I will first of all measure the diameter at this position of the candle here. Okay, like this. Now, as I was saying, as we did on the mainstream here, the fixed part of our vernier caliper, I first of all read the scale of the fixed part of our vernier caliper here. We are having exactly 10, 11, 12, 13, 14. I will not take 15 because 15 is already on the side of the movable part of my vernier caliper. So I will stop exactly at 14. So I'm having already 14. Then I will now go and look on the movable part of my vernier caliper. The number that is aligned with the fixed part of the vernier caliper will give me what? The two decimal places that are neat. So let us see. We are on 10, 11, 12, 13, 14 point. Let us see which number aligns directly with the scale of the fixed part. I think it should be okay. Try to observe very well. It is 6. Yes, it is 6. So I think the reading will be 14.60. That is it, 14.60. Now that is, well, let us name it D1. So that is our first diameter measured. The first diameter measure, let us say D1 equals to 14.60 millimeters. Okay, now let us change the position. Let us choose another position to make sure. We don't know if the diameter is constant. The cross-sectional area of the diameter is the same. So let us find D2. Now here we still have 10, 11, 12, 14. Yeah, we still have 14. Then the decimal place now will be at let us see which number aligns with the one up. Which number? I think it should be 8. Yeah, I think 8 align. Yes, 8 align. So will be, since it's only 8, I'll put 14.80. Like if we're maybe 8, if let's say here 8.5, here is 8.5, here is 9. It means that the reading will be 14.85. Yeah, because the moving paper is giving us the reading in 2 decimal places. Is the reason why you are putting here 0.05 millimeters. But since it aligns directly with 8 only, and I should respect the accuracy of the instrument, therefore I should put my D2 to be 14.80 millimeters. So that is the diameter of our candle. Then I would, since I'm having 2 values, I will go and calculate the average after. So with the value of the diameter, we can proceed with the mass. We can calculate the mass of the candle. Now for the mass, we are using an electronic balance. Okay, we on it, you wait. Okay, you wait until 0.00 gram come out, then you put the candle. From there you have exactly, so the mass is given exactly let me put it like this, 26 point, it's changing because I'm just from, okay, 26.38 grams. So that is it. So that is the mass of the candle. With the mass of the candle, we are left to calculate the length. Let me off the balance. We are left to calculate the length, yeah, the length of the candle. With those 3 data, we can now proceed and calculate the density of the candle. Okay, let me place the 0 here like this. Yeah. So if I want to calculate the length here, you see that it's exactly positioned at 19.1. So 19.1. So the length of the candle, which is the height, is simply 19.1 centimeters. Okay, students, now let us continue with station 2, determination of the speed of sound in air. You are provided with a turning fork, a plastic pipe, a transparent 250 milliliter measuring cylinder, and a metal roll. Use these to determine the speed of sound in air. So now, from the equipment that have been provided, we can also see that what we are asking to measure the speed of sound in air by method of resonance tube. So that is it. So without wasting time, let us come out with our diagram. I think the diagram should be quite easy. You should first of all represent you represent your, I don't know if you are using a beaker with water inside. Should represent it here like this. Yes. Okay. Then you represent your pipe, your plastic pipe. You should represent your plastic pipe, something like that. Okay. We know that the plastic pipe is opened at both ends. Okay. When you represent a plastic pipe, you represent the level of water. Just say here. You don't waste time. You represent your turning fork. You represent your turning fork. Let's say this is the turning fork here like this. Okay. Now. Okay. So there is it. You present your turning fork. You present yeah. You also represent the first overtone. Let's say the first resonance. And for an open pipe, the first resonance will be formed somewhere here like this. You should know it. The fundamental. In fact, the first sound will be getting somewhere here. That is called the first harmonic. So that is it. And we all know that what this one is a note, and this one is an anti note. Then you measure now the distance. You represent that distance, the distance from the level of the water to where is your turning fork, and we name it H. So there is your diagram. Forget to precise that this is water. Precise that this is water. Don't forget to precise that this is your plastic pipe. Plastic pipe. So there is it. Okay. Then let us proceed with the procedure. Now the procedure. For the procedure, we all know that what you are, in fact, you are describing your diagram, your setup. So you can say some water is poured into the measuring cylinder, and the plastic pipe placed vertically in it, exactly as we are seeing here. So you are describing, or another student can even say the setup is mounted as shown above. That is it. Then you say what you are doing. I'm supposed to measure the length as from where I get the first sound. So that is it. So I will say now the turning fork is struck, placed above the upper, is placed above the upper end of the pipe, and both are simultaneously moved upward until a loud sound is heard. Then the length of the air column is in the pipe is measured using the metal rule. That is it. So you are describing, it means that I will hit a turning fork, I will put it here, I will put it at one end of the plastic pipe, then I will adjust the length. I will adjust the length of what? I will adjust the length of the plastic pipes until I hear a loud sound. Then I measure the distance from the outer part of the plastic pipe and where is my turning fork. So there is it. So let us put it here. So the turning. The next is the length. Don't forget, the length should be measured. The length of the air column. The length of the air column in the pipe is measured. There is another one mark. The length of the air column is measured. Don't always precise using a metal rule. So these are where the 2 marks are coming from. This step, the length of the air column is measured using the metal rule, and the other step where you talk about the adjustment of the plastic pipe, so that until you hear a loud sound, those are a loud sound. Those are where the 2 marks are coming from. Now for our observation, we all know that what when we hear a loud sound during the experiment, that sound should give us what we call L, the length is okay, L, and we all know that the first position of resonance, if you are neglecting maybe the N correction, will be L equals to lambda out over 4 for open pipe. So people should know that. So this implies lambda should simply equal to 4L. So I will have this implies lambda equals to 4L. This implies lambda equals to, now from the L that you determine during the experiment, yeah, I think for us here L will be 16. Okay, so I will take 16 into 4 times 16 centimeter, don't forget. Okay, so by multiplying I will have 16 times 4, which is 64 centimeters. Okay, there is the value of L, and we also get the frequency because we need a frequency, and the turning fork was having a frequency of 512 Hertz. So those are the two observations that you get at the level of the station. Yeah. Then calculation, we all know that what? For the calculation, that one will be quite easy. We all know that the speed of light, so from V equals to lambda F, but I know the value of lambda, but I know that lambda is equals to 4L, which is equals to 64 centimeters. So the speed of sound in air will be simply equals to 4L F, which is 64 centimeters times 512 Hertz. So after okay, if I want the speed in meter per second, it's better for me to change this to meters. So I'll have 64 times 10 to the how many? -2 meters times 512. So making the speed of sound to be 227.68 meter per second. So that is it. From calculation, we are having this. It means that we can approximate it to 300. We can approximate it to 330. 229 meter per second. So normally the real value is 330 meter per second. The speed of sound normally is 330, but we are having 229. So it's an experiment. We can still do some errors. Okay. Now for the precaution here, you can choose any precaution that you want, and the conclusion is that the speed of sound in air is 329 meter per. It's approximately that. So that is all about station 2. As easy as that. The precaution, you can take anyone. You can even say that the station is visited. In fact, you see that the station the hall should be quiet so that the sound, the first resonance should be obtained easily. Yeah, the first sound that you are hearing should be heard easily if the hall is quiet. So any precaution. So that is it. Now let us move to station 3. Station 3 is the determination of the mass of cold water by method of mixture. Okay, this experiment you probably know it already in physics. It's not difficult. So you start directly by the setup. Yeah, the setup. I think here we are having a plastic cup X containing an unknown mass M, a fresh water, a plastic cup Y containing 25 grams of hot water, a thermometer, a stirrer, a lid with a holes for thermometer, and stirrer, that should be calorimeter. Use this to determine the mass of the fresh water. Okay, it means that I first of all draw my calorimeter here. Okay, I will draw my calorimeter. I can put the calorimeter can be closed, but it can have two holes to represent where I can put the thermometer like this, where I can put the thermometer. Another hole where I can put the stirrer. Another hole where I can put the stirrer like this. Okay. So there's it. Then I represent the level of water. Then I name it. Here should be water. Here should be the thermometer. Okay, this one should be the stirrer. And here should be the lid to cover. So that is it. That is it about the diagram. Okay, now the procedure. For the procedure, you are stating what you are measuring. Don't waste time. It's okay. So you can say that the setup is mounted as shown below. Then you are stating what you are measuring. Like I should measure what. Now, to let us come back here on our rough paper. I know that I want the mass of hot water. Okay. Now it's a mixture. I know that heat loss by hot water should be equal to heat gain by cold water. Is okay. And from there, another the heat lost by hot water is simply equal to the mass of hot water times specific capacity of water. Then he's losing heat. So he's losing heat from theta of hot to a certain theta final. Then mass of cold water, specific capacity of cold water. Then he's gaining heat. So he's gaining heat theta minus theta cold. So we see that here, this one will cancel. I will need to calculate theta of hot water. I will need to calculate theta of cold water. I will need to calculate theta, the final temperature of the mixture. So those are the three parameters I need for this experiment. When already you know that, from there you can come up with your procedure. So your procedure will be to measure the initial. So I will say the initial temperature, the initial temperature of theta H and theta C of the hot and fresh water are recorded. So that is it, or are calculated. I measure using a thermometer. So the initial temperature. Now, then after measuring it, I should now the hot water should be quickly now added to the cold water inside the calorimeter, cover, and then the temperature should be, the final temperature should be measured. Okay. Then the mixture is gradually stirred until its temperature becomes theta become constant. So into the final temperature you are measuring become constant. Therefore, you record it. So after now this, we go at the level of the. We proceed with the observation. Now the observation here. I need to go at the level of the station, calculate the initial temperature of hot water. I need also the initial temperature of cold water. You know, it's measured in degrees Celsius. I will need what again? I will need the final temperature of the mixture. Okay. Then the mass of hot water has been given, which is 25 grams. Okay, so that is it. I will need this one. I will take it from when I will go and collect the data. Now for calculation, it's exactly what I was saying. For calculation, I know that energy given, I know that the energy given out or given off by hot water should be equal to the energy gain by cold water. Should be equal to the energy gained by cold water. So that is it. So I will take mass of hot water, specific capacity of water, in bracket theta of hot water minus theta should give me mass of cold water. Specific capacity of water is T water. Theta minus theta of cold water. So by making the mass of cold water here the subject, I will simply have mass of hot water theta H minus theta divided by theta minus theta C. So that is it. So this is a formula. Then when I finish to collect data, I will come back now and put it here for us to have the numerical value of the mass of cold water. Okay. So any precaution here, you can say the stirrer is used to ensure uniform distribution of heat. So and at the end, the conclusion, the mass of fresh water or cold water, is okay. So now let us go now and collect our data so that we should come and finish our station. Students, so as I always say, at the level of the station, you are taking the data. So you should not waste time. You should know already what you are coming to collect. As I'm saying, from the reference we did already, we all know that for station 3, we need the initial temperature. So we need data for cold water, we need data for hot water, and we need the final temperature of the mixture. So these are the 3 data that we need for this station. Okay, now our main instrument here is the thermometer. So you should know how to read the thermometer here. So I'm seeing the scale here. This is 0, so it means that this should be 10, 20, 30. So it means that it's going 1 by 1. So 10, 10.1, 0.2, 0.3, 0.4, or pardon, 10, 11, 12, 13, up to 15, then up to 20, and so on. So I will first of all I will measure the temperature of hot water, the initial temperature of hot water. Put it like this. I wait that the temperature, the length of the thermometer will increase until it become constant. From there, I measure the temperature of hot water. So if you bring in here, you will see that it's already at 40. Okay, it's no more increasing. Okay, so it means that it is 40 degrees Celsius. Then from there, I measure the temperature of cold water. Measure directly the temperature of cold water. I measure the temperature of cold water. When you go in here, you see that the temperature is falling. It's falling. It's falling. So it's at 30. It's falling. Okay, it is at 30. It is at 30. Then, without wasting time, we immediately pour the hot water with cold water. Okay, then you close it. Then you measure You use a stirrer to stir, then you measure the temperature of the final temperature of the mixture. Okay, you wait a bit. You wait until the temperature will become constant. Let us see. Let us stir a bit. Okay, let us bring it near. You see that the temperature is rising a bit. It was first of all at 30, now it's at 30, 31, 32, 33, 34. 34. Let us see if the temperature will stay at 34. Let us wait. We turn it a bit. We turn it. Okay. We turn it. Okay, let us come and see. It is still at yeah, it means that it is still at 34. It means that the final temperature should be 34. Then make sure you record it. Okay, temperature of cold water. Of hot water it was 40 degrees Celsius, cold water 30 degrees Celsius, and final temperature 34 degrees Celsius. So these are our data for station 3. With these data now, immediately you finish to collect your data, you go back to your mainstream, then you fill the observation, then you calculate, then you conclude. So that is all about station 3. Okay, so after collecting our data, we can all see that the temperature of hot water here, the temperature of hot water is 40 degrees Celsius. Temperature of cold water or fresh water is 30 degrees Celsius. Temperature of hot water 40 degrees Celsius, cold water 30 degrees Celsius. Okay, the temperature of the mixture was 34 degrees Celsius. So that is it. So from those information, we come and replace it here. When you come and replace it here, we will have you have 25 grams into 40 degree minus 30 degree, all divided by 34 degree minus 30 degree. Okay, so that will give us 37.5 grams. So there is a mass of the fresh water. So I will come and put here my 37.5 grams. Okay, so that is it for 10 marks. That is all about station 3. Now let us go to our last station, which is station 4. Okay, station 4, investigate how the amount of light falling on an electrical component affects the current flowing in a circuit. Okay, now we want to investigate how the amount of light flowing on an electrical component affects the current flowing in the circuit. So you are provided with an electric component H, a battery in a holder, a multimeter set to DC 20 milliamperes. Use the component provided to find out how the current which flows through the component H is affected by the amount of light falling on H. Okay, so here it means that H should be what? A light dependent something. It should be a light dependent resistor. Pardon. It should be a light dependent resistor, because if you want to study how the amount of current varies as light, the amount of light falling on it also varies. It means that that the resistance of that component should depend on the amount of light falling on it. So we all know that we should draw a circuit here. For the diagram, we are doing a simple circuit in series because we are measuring current in series. So you draw your component here. You don't know, you will name it component H. You put your ammeter, you put your battery. So as easy as that, you don't waste time. So this is your ammeter, this is your component H. This light falling on component H. So indicate that this is H. Ammeter, this is the battery. Okay, that is it for 2 marks. Easy. Okay, Then for the procedure, you know what you're supposed to do. You know what you're supposed to do. H, comma the battery, H, comma the battery and the ammeter are connected in series. That is it, exactly as we are having here. Are connected in series. Okay, then we all know that what, so we are supposed to do it when the amount of light falling on it, when it is exposed to light and when it is not exposed to light. So I will come here, I will say the reading of the ammeter is taken when S is exposed to light. So okay, then for the last one, and the reading of the ammeter is still taken when H is block or when H is not exposed to light. It's about the procedure. Now, at the level of the, we will now move to the observations. The observation, you are going there to measure the current flowing in the circuit. So, you take maybe you name maybe it I1 and then you name it I2. It's okay. Where I1 will be the current when it is exposed to light, and I2 will be the current when it is not exposed to light. Now the inference here, very easy. The inference here, we all know that what, if the current reduces in the circuit, therefore it means that what, the resistance of the circuit had increased, and if the current increases, it means that the resistance had decreased. That is all. So that is the inference. So the inference will be when the circuit resistance is high, less current flows in the circuit. Yes. So now when the circuit resistance will be low, so when the circuit resistance now will be low, more current will flow in the circuit. Now the precaution here, you can take any precaution that you want. You can take any precaution. Make sure that the connection are well. Let's say what, film or what. Let's say the ammeter. Make sure that the multimeter is set to the ammeter reading. So all those things depend on you. Now the conclusion now. For the conclusion, okay, for the conclusion now, it will depend on our values here. It will depend on how the current varies. Here depends on the amount of light falling on component H. So let us go to collect our data and then come and conclude.
Okay, student, as you people can see, the main equipment here for this station is a multimeter. So if you don't know how to use a multimeter, you cannot do the station. So as I was saying, the multimeter is divided like in how many sections? 1, 2, 3, 4 sections. Yes. And here we are having the entries here. We are having AC, AC 10 ACD, and we are having com here is like the neutral. So it's always preferred to put the black one here and the phase, this one, the positive, to be here. Okay, now here this section DCV means direct current. Yes, direct current, and it measuring what, the voltage. As the name says, multimeter is made up of many meters. Yeah, here is a voltmeter which measure direct current. Here is a AC voltage, so AC current which measure AC voltage, alternating voltage. Now here this section is a DC current, so it measure what, direct current in amperes. Here is in micro, milliamperes. Here is directly in amperes. So if I put it here like this, I'm measuring directly in amperes. And this section is ohms, in measuring what, the resistance. Okay, now these one are the different calibrations. Yes, so like you're seeing from 1220 2200 milli means millivolt. is the calibration. It depends on what you want to measure. If I maybe put it at 20, it means that what I want to measure is slightly equals to 20 volts. If I put it here at 1000 volts, it means that the calibration at 1000 means that what you want to measure should be around that value. So that is it. So this is a brief explanation of the interface of the multimeter. So that is it. Here, this DC, we want to measure direct current. You are seeing here 2000 micro, 20 milliamperes, 10 amperes. So these are the different calibrations. Okay, so in this station, the multimeter is being used as an ammeter. It means that you want to measure the current flowing through component H. So you want to compare when component H is exposed to light, how does the current varies? When component A is not exposed to light, how does the current varies? So is what you want to do here. Now, the first thing that you should know here is that how do we connect an ammeter in a circuit? An ammeter is always connected in series. In a circuit, you should know how to do series connection. Series connection is not parallel connection. So you are supposed to take this your battery. You take one terminal of component H. You connect with one terminal of the battery like this. Then, for you to have a series connection, you take also one terminal of your multimeter. So this is it. You connect to one like this, and then you take the other one, you connect to the other terminal, which is alone. This is a series connection. We understand this is series connection. Then I should set my multimeter to the ammeter. So the ammeter set to 20 milli. The precise, they should set to 20 milliamperes. So I'll put it like this. I'll try to measure. Now don't bother about the negative. It means that I interchange the positive terminal with the negative one. So you measure the current. This is when component H is exposed to light. Pardon. You can see that it's 2.95. Let's say 2.95 milliamperes. Why am I saying milliampere? Because the calibration at the level of the direct current we are measuring is 20 milli. So it means that any value they are taking there should be in milliamperes. So let us see, has varied. Nice. Let us see. Yeah, when I expose it to light, you see it is 2.92. So you come indicate a station 4. So the first value of the current, you can name it I1, is 2.92. This is when H is exposed to light. Okay, we do same when H is not exposed to light and C. So I'll do by doing the same connection, the series connection. This is it. It's still series connection. Look at. So then this I'll put my finger like this so that our component H is no more exposed to light. You see that the current flowing through component H now reduces to 0.39. It means that what? It means that when I block or when I hide component H from light, the current flowing reduces. So it means that the resistance of component H increases, therefore reducing the current flowing through it. So I'll take 0.39 milliamperes. So I'll come here, I'll record it directly like this. My I2 is simply equal to 0.39 milliamperes. Pardon, I forgot the milliamperes always. This is when H is not exposed to light. So as easy as that, you have already your observations.
Okay, students, so after collecting our data from the level station, we all saw that I1 was 2.92 milliamperes. That is when H is exposed to light, but immediately H was blocked, or H was not exposed to light, the current dropped to 0.39 milliamperes. So this is when H is not exposed to light. So that is it. Then from there we can now do our conclusion. That is it. From there we can now do our conclusion that when H, we also that when H is exposed to light, its resistance is low because more current flows. So when H is exposed to light, its resistance is low, and when H is not exposed to light, its resistance is high. So that is it for 1 mark. Okay, students, so that is all about the Northwest. That is all about the Northwest Regional Mock Paper 3 Physics 2026. So you people should subscribe and be ready for the upcoming other practical sessions. So thank you for watching our videos. See you later. We are together.